Oh, yay. Okay, linear transformations. I told you you need to study this for the test, and there was a reason. It's because we're actually covering it within this chapter. And so we're going to talk about the effect linear transformations have on moving figures around the coordinate plane, and how the determinant will help us with those effects. So if we have a linear transformation determined by a 2x2 matrix, so we talked about linear transformations in chapter 2, and what we're going to be transforming in this blurb is just a parallelogram. And one thing that's really useful is that if you find the determinant of the transformation matrix A, which is what you multiply, for example, this by, it will tell you what effect it has on the area in the volume. So if the determinant of the transformation matrix is not 1, what that indicates is that the area is modified by that factor. So if your shape originally, your polygon originally has a magnitude of 14 or an area of 14, and let's say you multiply it by a transformation matrix, and the determinant of that matrix is 2, that would mean the area would be doubled as a result of doing that transformation. So this is yet another case where determinants are useful. They're geometrically useful. Likewise, we have the effect on volume, and we're talking about a parallelepiped. When we talked about taking absolute value yesterday, we were discussing how in this setting area is only considered as positive. But if you get a negative determinant, while the area is still going to be affected by multiplying it by the absolute value of that determinant, what it means regarding the transformation of the shape is that the orientation is changed. So for example, if I were to name these vertices in this example, A, B, C, D, if you have this multiplied by a matrix that transforms it, and the determinant of that matrix happens to be negative, what that means is that this orientation has been flipped, meaning it would go from like ABCD to ADBC. Sorry, ADCB. Yeah, that's right. So changing orientation means you flip the shape. And so an example of this, I like using color to show that, because if you just show a parallelogram and then you show it again, you can't tell orientation. But if you use color here, it becomes really useful. So if we take a look at this 1 by 1 squared, and we multiply it by this transformation matrix, this is what happens to it. Do you notice how the orientation is flipped? It goes from blue, yellow, green, red, going around clockwise, to blue, red, green, yellow, going around clockwise. So this must have been taken out of the plane and flipped it through the transformation. So a negative determinant shows you that that has taken place. Any questions? Okay, so this applet is really cool. That's the one where I stole that image from. So we have determinants and linear transformations. That's our topic today. This shows for 1 by 1, and then this would be, let me do a little zooming. For example, if you multiplied by the matrix -2, 0, 0, -2. So you can see that the 2 scales the matrix in the X and the Y, And the negative flips the orientation of the matrix. So it's flipped over the x-plane and over the y-plane. And so it has been flipped twice, which means the orientation actually is still the same because it's been flipped twice. It was flipped over the x and over the y, or you can consider it as also a 180 rotation because that accomplishes the same thing. But if we only had flipped it over one, it would have a negative orientation. In this case, we flipped it twice because the x is negative and the y is negative, so the x being negative flips it over the y negative flips it over the x, so it ends up with the same orientation, but the area is affected by being multiplied by 4. And the determinant of this transformation matrix A is 4. Let's see that. So that's a pretty straightforward example of that. Any questions so far? All right, so take a look at this one. This one right here. This one, you can plug any matrix in. It's kind of fun, and it will transform it for you. So you plug in whatever matrix you want, and it does the transformation. So I want you guys to take a look at the matrix, and you have the visual, and I want you to figure out what transformation has taken place. What have they done to it?
They flipped the x values and then also subtracted the y value and put it in the x. For the x value.
So they flipped over which axis? So say in terms of
Over
geometry.
the y-axis.
Flipped it over the y.
And then they took the value of the y coordinate
Okay.
and subtracted that from the value. So like if you had the 0.22, it would become -2, 2, and then you would also subtract the y value, which is become -4.
Okay. But I'm just thinking in terms of geometry.
Oh.
Like I definitely believe you about the flip because we're in this quadrant over here, like at least the left side, and also the orientation has flipped. So the flip had to have occurred, but I'm just trying to think geometrically what else. Right? What were you going to say?
So they flipped it, and then I think they transformed it down by 1, and then rotated it by 9.
Can we transform with the 2 by 2?
No, well, you don't use 3 by 3, I guess. Well, that's not.
Mark, which?
Then like, either like move it and then scale it up by, or like rotate it up the y-axis and then scale it up by like a factor of 2 and then rotate it.
So you're saying flip it, move it, or flip it, rotate it, scale it, or what was your order?
I would say flip it, scale it, rotate it.
Okay, so try on your paper to develop the multiplication chain of matrices that occurred. Is it a reflection? Is it a rotation? Is it a scale? You guys know how to do those from when you presented way back when. But what chain of single transformations would generate this? -1, -1, -1. 1 is the resulting matrix. If we all agree we flip first over the y, flipping over the y means you make the x negative. So that's we flip over the y. So if that's done first, we put that to the right. That's first. But then what's second? And what's third? And then does it end up being that? So mess around with it a little bit. See what you can come up with. Now, who wants to volunteer what they got? Rohan.
2 over radical 2, 0.
Okay, so tell me the first,
Oh.
second, and third.
So the flip over y, the first one,
Okay,
and then the second one is the rotation by 45 degrees.
so what was that matrix?
Radical 2 over 2, negative radical 2 over 2, positive 2 over 2, radical 2 over 2.
Okay, and then what was your last?
Radicals, so that was like the scalar
By what factor?
by that, or 2 over.
Now 2 over radical 2 is the same as radical 2.
Yeah.
So if you want the area to increase by 2, and you want it to be spread out amongst the same dimensions, the x and the y, then each would have to get the square root of 2. Because the x's are increased by square root of 2, and the y's are increased by square root of 2, and the net increase would be square root of 2 times square root of 2, which is 2. So what would this matrix be, Rohan?
Radical 2, 0, 0,
Okay. And so that, when you multiply it out, should equal this. So you flip, which would put it here. You rotate, which puts it here. But it's only 2 units long here, this part, this 45-degree rotation. But then you have to make it so that this diagonal is 2 radical 2 units long and not 2 units long. Because if you consider this right triangle here, this is 2 and this is 2. So the vector went from being 2 units long to 2 radical 2 units long. Jeffrey?
But like if the area is 2 times bigger, wouldn't the scale be 2 instead of radical 2?
So if you increase both the x's and y by 2, what is the whole
I
area?
think the determinant that would be 2.
Correct.
Okay.
Other questions? Right?
The order doesn't matter in this one, right? Just do them.
I think, and Mark was asking about this as well, I think you can scale whenever. I think the thing that matters is whether you flip first or rotate. Because if you rotate and then flip, think of rotating this 45 degrees, it would look like a diamond, and then flipping it over the y, it would look identical. So the order here, you have to flip first, but I believe you can scale at any point. Because you'll still have that anchor at 0, 0, which would keep the flipping the same and the rotation the same. Other questions? So, yeah, this was it. Okay. So, go ahead and tell me whether the orientation's changed and how the volume is affected for this one. If A is your multiplication that achieves the transformation. Once you get the determinant, you may want to check with a classmate to see if you guys got the same thing. anyone else get 8?
Well, the first one would be 10. A plus or minus 1 is 10.
Huh? Thank you. So the determinant is 10. Yeah, 12. So the volume is increased by a factor of 12. And is the orientation changed?
There's a no negative sign that we need the same orientation.
Great. Great.
So if the orientation changed all like 1 degree or 360 degrees, it would be negative.
It's just indicating that there's been a flip. It's not a rotation. Rotation doesn't change orientation because you're still in the
Oh, yeah.
plane. You have to take it out of the plane in order to achieve an orientation. Or out of the three-dimensional space. I don't know what this looks like for about, I mean, I suppose you just turn it inside out, kind of. All right, so big homework assignment.
That was